Hi, Rashid here. Welcome to the second part of the revision of week 4 and mostly 5. In part 1, I covered most of the other things, and in this part, I will cover mainly IO constraints. But before I start going into detail of IO constraints, one thing that I missed in the last video was giving you very quick summary. I won't take too much time of the report annotated parasitic report that we reviewed. So once we read in spef file, okay, our goal was to look into this report to make sure that we have a good idea of how many nets are annotated with those parasitics that we are reading and how many are not, or what other issues are. This report annotated parasitics, is a very important report. It gives you a lot of information. Actually, it covers a lot of the things that you're going to find even in the log file when you're reading parasitics. So the report covers different category of nets. So it's split nets into different categories. One is assign. Assigns are because of the assign statement in your netlist. So these should not be there. We will remove them in the future netlist, or try to remove them in the future netlist, and we'll see what happens if we don't. Floating are the ones they don't have any driver, they don't have any receiver. Some of the metals are lying there. Okay. Then danglings mean, okay, they don't have a driver or they don't have a receiver. Okay. All these categories will be reported as not annotated, and these are the real nets that we have. They have a proper driver, proper receiver, and then tool is going to split them into what percentage of total nets are properly have parasitics in the spec file and how many not. So we had very small number that didn't have, and we look into that and found the reason. And another category that in the report is zero capacitance nets with no capacitance at all. Okay, so these are also reported, and we look into those ones too. We also look at a quickly example of one of the nets from spef file, just to understand the syntax when you are looking into mismatch between spef and actual. You can at least look into and make some manual looking into the spef file and make some comparison, simple comparison, right? So a name mapping section of it, then connectivity section of it, where are caps defined, where are resistances defined, those things we'll look at. All right, so that's something we did. Sorry, before I had to go into IO constraints, we had to look into that. I think I covered. All right. For IO constraints, I want to show you this path. This is an example path. So what you have a 1-bit flip-flop where launching the data, and then you have 3 combo cells in between these 2 flops, and we have a second flip-flop. So 2 flip-flops, 3 combo cells. Then the first flip-flop getting its D input from outside. Imagine this is our chip, or this is your block, and this is coming from outside. The output from the last flip-flop is going outside. First of all, you read this netlist into your STA tool, and you have timing libraries for this information within for getting definition of flip-flop, different timing hours, all this information in the timing library. You link the design. Linking went fine, no problem. Now the next stage is you want to run check timing, or you want to do report timing. Just analyze without any, let's say you even read a spec file, you have a resistant capacitance for all these wire segments there. Okay, now you need to analyze timing. Okay, when you do report timing without any clock definition, tool is going to give you unconstrained endpoints. It tells you there's nothing constrained. Okay, so we look into, you need to define a clock, because remember these will appear as unclocked. So you need to define a clock. So clock definition will have a period, right? And then we will also have Okay, where is clock coming at? So remember we did a create clock dash name dash period, and we defined the pin or port where we created this clock, right? So once you define this clock, then you do a report timing. So this path, do report timing to this, and you will see this timing path reported. And when it report, there is an endpoint. Endpoint is this D pin, and there is a launch. This is the launch point. Assuming there is no clock tree delay, there's no network delay. This is just right now an ideal scenario. This clock is connected here and here. Right, so period of the clock is there. So, tool will calculate setup and hold time on this endpoint, and your start point is this one. All right, this is the D pin 2. This is a valid endpoint, right? So what if you do report timing to this one? And report timing will tell you this is not constrained. What's going on? You have defined this clock, but still it's unconstrained. What is happening? Well, on the capture side, yes, it knows this is the clock period. And based on the by the way, you also need to define a transition time on the clock port, or tool will default to 0 picosecond, or we've seen in the tool it probably defaults to 100 picosecond. So to based on that, transition time, let's say you want transition time here, then it knows transition time here, it knows the setup time of this flip-flop. But still it's unconstrained. I mean, you probably be wondering where input is coming from. It should give me a timing because this is a wire delay. There's no cell delay. So, but a timing path is with respect to, there's a launch clock edge or clock level, and there's a capture edge or clock level. In case of flip-flop, is edges, right? So capture you have, but launch, this clock is not connected here. Actually, tool doesn't have any information about this, which clock to consider, from where this data is coming from, on which clock it's launched. Okay, so how do we determine that? Yes, so this is the input timing path, and this one. So in situation reality, this logic that is somewhere was launched. This we're talking about synchronous design. So somewhere it could be, let's say in our case, this was an SoC. So there's another chip on the package. Sorry, not package, on the PCB. So this chip goes with the PCB. Its data is coming from another chip. Data could be coming from the IOs. Data could be coming from maybe from the computer UART. Some sort of communication happening. So somewhere it's launch on something. This data is coming with some sort of reference. Okay. Now in case of source synchronous, that's a different story, your clock data. But let's talk about this particular sort of synchronous design. So data is coming from with respect to some clock, and clock comes here. So it's a latch of flip-flop. Let's assume it's a flip-flop. It might have some combination. We don't know. Maybe nothing. So the timing path comes into the real timing path is from here. But right now you are still here. You don't see this picture. So you need to model some sort of delay here. You need to tell the tool from this point outwards, this was a delay and that was the clock. And then tool will have a picture to make a timing report. It will know that, okay, it doesn't need to know which kind of flip-flop, but all it needs to know is which clock it is, and with respect to clock rise edge or fall edge, how much is the delay here. That's it. And that exact information, when you provide this, here's the syntax of an STC. Okay, in the case of this clock that you give, this is not inside your design, it is outside. Right, and you define it with create clock dash period, you give it name, but you haven't defined it as which port or which pin, right? Remember the other clock that we defined in previous video? So that's why since it doesn't have a source, it's called a virtual clock. It's outside, it's a virtual one for you. And then you define a delay at this point, set input delay because it's input port 100 with respect to this clock that you define here. How much this clock, set input and on which input this port in. So now it tool knows that there's 100 whatever nanosecond, picosecond in respect to this clock. You define this clock so it knows this period. From a period it knows the edges, rise, edge, fall. You also okay, another thing. So you have defined that one. So now your constraint will be there. Now your path will be constrained. But you know that the two things that tool calculates. One is the arrival time with respect to something, of course, with respect to clock, how much is the time here. Also transition times are calculated along each node on a timing path. So tool needs to know what kind of transition time you have. If not, it might default it to some unrealistic value. So one way is I define like this. This is my transition. This will be very ideal waveform. Another possibility is that you tell the tool, hey, just assume that this pin is kind of driven by a buffer or something like this buffer. Or maybe put a buffer that has a pretty bad delay. Right? So you say, okay, this is my kind of buffer, and if its input is 50, 100, 200, 800, depends on whatever you value pick, then tool will calculate through this and will have a more practical waveform here. So here is now how to pick this constraint. Now here is the key thing here you need to understand. You are designing this chip. Outside, even if there are situations you can calculate this accurately, fantastic, no problem. You know exactly how much delay it is. Then use actual delay. But a lot of times we sometimes don't know. Or sometimes know but not with good accuracy. So in those cases, what do you don't have a control here, but you have control here. So put this flip-flop right next to it if possible. If there are combinational cells, okay, yeah, of course, still try to put as close as you can without creating, of course, any issues on this side, so that you have the least delay, smallest delay possible. In that case, if your chip is next time used in another PCB where this chip is further away from this, you're not breaking still. Because you did your best to constrains your input. So in some of those cases, in my example, for example, I put 8 nanoseconds for outside, 2 nanoseconds for myself because my clock was 10 nanoseconds. I can even do 1 nanosecond and 9 seconds this one. So I'm preparing for the worst scenario. Later on, if I tell somebody it should have internally 3 nanoseconds and they will be restricted. So I don't want to be my chip want to be the bottleneck, right? Don't want to be the bottleneck. Sorry if I said yes. Want to be the bottleneck. All right, same exact story with the output. Same concept apply here. This time you put an output delay here and your virtual clock is here. So you define an output delay here. Everything else is same. The only other difference is instead of driving with transition time here, now transition time is coming from here. This transition will depend on transition here. Okay, so but your transition time, what you don't know how much capacitive load this is, because that will have a loading impact on this cell. So just again make some guesses, accurate or less accurate, and see what kind of capacitance it is and use that as set load, whatever that is. By the way, you can get a unit of capacitance and time and resistance and all that within your STA tool. So get that and define that. So that tool when calculates actually timing, because timing here depends on how much capacitive load is here. Timing through this one. All right, but concept is same: input, output. And then you also have, we didn't have this scenario, but sometimes you can have, if for example you on a block in an SOC. Now input is coming from it, is going output to connecting to another flop. Your design at the top level, you don't have any channels between. Everything has to go over within through the blocks. So in this case, as input comes, go through some buffers, maybe logic, maybe in case of some sort of stuff there, and goes output. There's no flip-flop involved. One way is you apply input delay, output delay. Another way is you also define a max delay here. So that's kind of a combinational constraints. A maximum delay needs to be this one. The tool will follow that if it can. So those are called feed-through paths. All right. I think with this concept, you should be able to understand what I was doing, and later on we will refine those icons more. All right, that's it for now. Thank you so much. See you next time. Bye.